Hello, this is Professor Kuehn. Welcome back to my lectures on Einstein's theory of special relativity. You might remember that when we began these discussions of relativity, we started by talking about the addition of velocities, and we had a kind of a classical velocity addition formula where we're thinking about if, let's suppose, one person is riding in the back of a spaceship or a pickup truck, you might say, and they throw a baseball at a high speed. Let's suppose they were to throw it at 50 miles per hour. Then what about someone who's standing on the road alongside the truck? How fast would they see the baseball traveling? And we use this traditional velocity addition formula where you simply add the 50 miles per hour of the baseball to the 60 miles per hour of the pickup truck, and you would say that the person standing on the ground sees the baseball traveling at 110 miles per hour. That's the traditional formula for velocity addition. What I'd like to do in this lecture is talk about how there are some problems with this velocity addition formula that arise when considering special relativity, Einstein's theory of special relativity. And what I'd like to do is develop or tell you what a new velocity addition formula is that is consistent with Einstein's theory of relativity. So let's go back and explore relativistic velocity addition. So relativistic velocity addition. This, by the way, the reference is, this is treated in a student's guide through the grade physics texts, volume 2, chapter 31. Okay, so let's remember what we had been doing before. Let's suppose that we have a pickup truck, and let's suppose that you have someone riding in the back of the pickup truck. I know I talked about these persons as Matthew or Mark or John. Let's use a little bit different terminology. Let's call this person 2. You'll see why I'm doing this in a moment. And he throws a baseball, and that's object 1. And so he throws it at some speed. Let's call u12 the speed of the baseball, or we might more generally say the speed of object 1 with respect to object 2 or person 2. That would be like Matthew riding in the back of the truck. That might be 50 miles per hour. Then let's call the person standing on the road alongside, we'll call that person 3, okay? And let's suppose that the truck is moving at a speed u23. That would be the speed of object 2, that would be Matthew riding on the truck, with respect to object 3, that would be Mark standing along the side of the road. And what we want to do is have a formula for the velocity of object 1 as measured by person 3. That is the speed of object 1 with respect to 3. Okay? And the traditional formula that we had, the traditional velocity addition, which we are going to modify, by the way, which ends up not being quite correct according to the theory of relativity. The traditional formula was that u13 was just equal to u12 plus u23. Okay, so that's where we had started our discussions of relativity. Now remember what the problem with this was, is that if the person number 2 standing in the back of the pickup truck had a flashlight and he turned on the flashlight, it seems that if we took this formula seriously, then the person number 3 who's standing on the ground would see the speed of the light traveling away from himself as faster than c, because you would have to add the speed of the truck to the speed of the light to get something like 301,000 kilometers per second or something like that. And since we're taking the absolute speed of light to be a correct statement of nature, then that seems like there would be a problem with this formula. So what we're going to do is we are going to develop a new formula for velocity addition that works for baseballs and the speed of light, in fact, any object as measured from different reference frames. Okay? So, and just to highlight why this would be a problem, maybe I'll say one other thing about why this formula, the traditional velocity addition formula, is a problem. You might imagine, let's suppose that Matthew on the back of the truck has a really good arm, so that he is able to throw that ball at, so this would be if u12 was, let's say, 0.8 c. He could throw that at 80% the speed of light. And let's suppose that the truck was moving at a really high speed, 70% the speed of light. And this would imply that the baseball is moving compared to person 3 at a speed of 1.5 c if we were to use this formula, which implies that the baseball is moving at 150% the speed of light, which from the perspective of the theory of special relativity, this is a problem. Okay, so we want to have a new velocity addition formula that would not give rise to this problem. You might ask yourself, why is this a problem? Why can't things move faster than the speed of light? Well, that's a whole nother issue. Okay, so let's try to come up with a formula or talk about a formula that preserves this universal speed limit. Okay, so what I'm going to do is I'm going to simply write down the formula for you, and then I will show you how it works. Okay, so the relativistic velocity addition formula, which attempts to preserve this universal speed of light, looks like this. u13 is equal to, just like the old one, u12 plus u23, but then you divide it by this new factor, 1 plus u12 u23 divided by c squared. This will be the new formula that is consistent with Einstein's theory of relativity. I have not derived this for you. This is something that's derived in chapter 31 in A Student's Guide to the Great Physics text. That's from Einstein's book Relativity. And you can take a look at that if you like, but I'd like to just talk about this formula for now and how this achieves some of the goals that we would like a velocity addition formula to have. So first of all, let's go back to this example right here. And suppose that this person throws a baseball at 80% the speed of light, and the truck is traveling at 70% the speed of light. What would be the velocity that one achieves, or one calculates for the baseball according to observer 3 using this formula right here? So I'm going to kind of combine this formula with this previous example. So in that case, u13 would be, well, 0.8 c. That's the speed of the ball compared to observer 2, plus 0.7 c, that would be the speed of the truck compared to observer 3. And now we have this correction, 0.8 c times 0.7 c over c squared. Okay, so in the numerator we get our 1.5 c as before, but now in the denominator we get 1 plus, well, 0.8 times 0.7 is 0.56, and we have a c times a c would give us c squared over c squared. Those cancel, so you get 1.5 c over 1.56 c. I'm sorry, 1.56. Oops. Okay, and so u13, when we do this, I did this calculation, 1.5 divided by 1.56 ends up being 0.96 c. So notice that the baseball's speed does not exceed c. Okay, it's a different speed as measured by Mark, who's on the ground, than Matthew, right? So Mark would see it traveling at 96% the speed of light, whereas Matthew only sees it traveling at 80% the speed of light. But there's not a simple addition of the speed of the truck to the speed of the ball. We use this new velocity addition formula, and it retains the speed of the ball under the speed of light. Okay, now you might ask, well, why is this formula desirable besides this feature? I mean, you could have come up with all kinds of formulas that might achieve the same goal. Well, one of the nice things about this formula is that it preserves the speed of light at exactly c for both of these observers. So let's do another example. So example 2, I guess this would have been example 1. Okay, example 2, let's suppose that Matthew has a flashlight. Suppose that Matthew has a flashlight. Okay, and he turns this on. And so we're going to use once again this velocity addition formula to calculate the speed of light as measured by Mark. Okay, so u13 would be, I'll just tell you what this is here, the speed of the light as measured by, in our case, it would be Mark, observer 3 on the ground, would be, well, the speed of the light as measured by Matthew, that would be c, because he's turning on the flashlight, it's moving away from him, that's u12, right? The speed of the light moving away from Matthew. Plus the speed of the truck would be 0.7 c, okay? And we'll divide by 1 plus, well, c times 0.7 c over c squared, right? So if I were to maybe highlight this, this would be the speed of the light away from Mark, or as measured by, Matthew. Sorry, I hope I didn't confuse you there. Speed of light is measured by Matthew, who's holding the flashlight and turns it on. Okay, so in the numerator, we have 1.7 c. In the denominator, we have 1 plus 0.7 c squared over c squared. The c squareds cancel, and we get 1.7 c over 1.7, which means that the velocity of that light beam, according to Mark on the ground, is going to be, well, the 1.7s cancel out, and you get c once again. So in other words, this formula that we've just articulated here preserves this idea that the speed of light by both sets of observers is c regardless of their relative motion. In fact, that's how this formula was originally derived by Einstein. He tried to think of a formula that would preserve the speed of light. And then he took this to be the general formula for velocity addition. Okay? Let me say one other thing about this formula. Notice that in this formula, when the speeds are very small, this reduces to our traditional velocity addition formula. So if u12 and u23 are small compared to c, then this term in the denominator becomes very small because you have a c squared in the denominator and things very small compared to c in the numerator. So this term becomes almost 0. So you have 1 plus 0, so you just get a 1 in the denominator, and this reduces to our traditional velocity addition formula. So people who are studying things that are moving not near the speed of light can be forgiven, you might say, for using the traditional velocity addition formula. But this new velocity addition formula purports to be more general than the traditional one. Okay, now let me say one other thing before I end this discussion. There is sometimes another way that one sees this velocity addition formula that can be a little bit harder to work with calculationally, but it's a little bit easier to think about conceptually. So there's another way to write this, and I'll write it this way. C minus u13 over c plus u13 equals c minus u12 over c minus plus u12 times c minus u23 over c plus u23. So notice these same things appear in here. You've got the speed of light, you've got the velocity of 1 with respect to 2, you've got the velocity of 2 with respect to 3, and you've got the velocity of 1 with respect to 3. This formula here ends up being exactly the same in its predictions as this formula right here. So these are equivalent formulae. Okay? Now why would one use this formula instead of this one? Well, this one actually can be compounded. In other words, if you wanted to find the speed of 1 with respect to observer 4, you could just add on another term here. You could do c minus u14 over c plus u14 equals these two terms, and then you'd multiply by another set of terms like this. You could have c minus u34 over c plus u34. Okay, and that would give you c minus u14. Okay, so sometimes one will see this velocity addition formula, which you can just keep on adding terms if you have 2, 3, 4, 5, 6 different observers all moving with respect to one another. Okay, we will primarily be using this formula in order to solve problems. Okay, I'll stop there, and I think next time what I will do is I'll do one more example of how to use the velocity addition formula, and then we'll start talking about relativistic mass and energy.